Imagine you're training a machine to detect spam emails. The model makes predictions. But how do we measure how accurate or wrong those predictions are? That's where cross entropy comes in. It's not just about being right or wrong, it's about measuring how far off the prediction is and how confidently the model made that mistake. Cross entropy calculates the difference between what a model predicts and what the true label is. Suppose the true label is 1, meaning the email is spam, and the model predicts 0.9. That means it's 90% confident the email is spam. Not bad. The examples and formula we're using here assume a binary classification setup, where the true label is either 0 or 1, like spam or not spam. In multi-class problems where there are more than 2 possible classes, the loss function looks a bit different, using what's called categorical cross entropy. The formula of binary classification is loss equals negative open bracket I times log of p plus open parenthesis 1 minus y close parenthesis times log of 1 minus p close bracket. In this formula, y represents the true label, either 0 or 1, and p is the predicted probability for class 1. Let's take a closer look at how cross entropy loss behaves for different predicted probabilities when the true label is 1. This table illustrates 4 scenarios. In the first row, the model predicts a probability of 1.0 for class 1, which exactly matches the true label. The loss is 0.000, meaning it's a perfect prediction. Next, when the model predicts 0.9, it's still very confident and close to correct. The loss slightly increases to 0.105, which is still considered a good prediction. Moving to the third row, the prediction drops to 0.5, which shows uncertainty. The model is essentially guessing. The loss increases significantly to 0.693, and we classify this as an average prediction. Finally, in the last row, the model predicts 0.1, which is far from the true label of 1. This prediction is both wrong and confident, leading to a high loss of 2.302. We interpret this as a bad prediction. This table shows how cross-entropy loss grows rapidly when the model confidently predicts the wrong class, reinforcing the idea that confident errors are penalized more heavily. Graph visualization, curve behavior. This graph shows how cross-entropy behaves mathematically. The yellow curve represents the case when the true label is 1. As the prediction moves closer to 1.0, the loss drops toward 0. But if the prediction approaches 0, the loss shoots up dramatically. Mathematically, it follows the formula, negative log of p. The orange curve shows what happens when the true label is 0. It uses the formula negative log of 1 minus p. If the model correctly predicts a low probability, close to 0, the loss is small. But if it wrongly predicts 1, the loss becomes very large. These curves show us that the more confident the wrong prediction is, the higher the penalty. Key intuition and real-world examples. The key intuition behind cross-entropy is this: wrong predictions aren't all equal. If your model is unsure and gets it slightly wrong, the loss is tolerable. But if it's confidently wrong, it gets punished severely. That's what makes cross-entropy such an effective training signal. Let's look at 2 examples. First, if the true label is 1 and your prediction is 0.9, your loss is low. Great job. But if your prediction is 0.1 and you are confident, the loss will be very high. This encourages the model to not only be accurate, but also calibrated in its confidence. So far, everything we've discussed applies to binary classification, where the model predicts between just 2 possible classes, like spam or not spam. In these cases, the formula we use is simple. Loss equals negative y log p plus 1 minus y log 1 minus p. But what if we have more than 2 classes? In multi-class classification, like identifying whether an image is a cat, dog, or rabbit, we need a different approach. The label is now a one-hot vector, like 0, 1, 0, and the model predicts a probability distribution across all classes. Here we use categorical cross entropy, which sums the negative log probability of the true class. This is written as loss equals negative summation of y sub I times log of p sub I across all classes. In essence, both binary and multi-class cross entropy do the same thing. They punish confident wrong predictions, but the math scales as the problem becomes more complex. This table shows how cross entropy loss is calculated in multi-class classification, where the model predicts among three possible classes: cat, dog, and rabbit. Each row represents one input sample. In the first row, the true class is dog, represented as a one-hot vector, 0, 1, 0. The model predicts probabilities 0, 1, 0.8, 0.1. Since dog is the second class, we calculate the loss using only that class, negative log of 0.8, which results in a loss of approximately 0.2223. In the second sample, the true label is rabbit, encoded as 0, 0, 1. The model predicts 0.2, 0.3, 0.5. Since the true class is the third one, we take negative log of 0.5, giving us a loss of 0.693. The third row shows a prediction where the true class is cat. The model gives 60% probability for cat, so the loss is negative log of 0.6, which equals 0.5111. In the fourth and final example, the true class is again dog. The model is less confident this time, assigning only 40% to dog. As a result, the loss is higher, negative log of 0.4, yielding a loss of 0.916. This table highlights how cross-entropy punishes low confidence in the correct class and encourages the model to assign high probability to the true label.